Practical 3, whilst also including observing the microscopic structure of different materials, was focused primarily around the concept of fracture toughness. Through the method of applying a hanging mass to various types of tapes, all featuring a pre-induced stress concentration point cut into the side of the tape, the main objectives of the experiment were to observe and measure the effects of the different materials, their thickness, width, and the initial crack length, and how they alter the fracture toughness of such. The results of such observations, when applied to the correct fracture toughness equation, should produce a numerical value for fracture toughness that allows different materials to be compared regardless of their geometric proportions.
For the electrical tape, we had tested it for fracture toughness. We had decided to put a slit into the side of the tape which had a width of 5.5 millimeters. The electrical tape had a thickness of 0.13 millimeters and a width of 17.3 millimeters. When the test was carried out, multiple weights were added till the tape failed. The electrical tape failed at 1.3 kilograms of weight, which results in 12.753 newtons of force acting on the tape. From this, we were further then able to calculate a value for K1C, which resulted in the value of 32.5, therefore implying that the electrical tape had a critical stress intensity factor of 32.5 megapascals times the square root of meters. We had chosen to add a side slit to the tape because in the equation for K1C, having a side slit results in more stress on the tape.
Duct tape was now to be tested for its fracture toughness. We again decided to have a side split to minimize the mass needed. The duct tape had dimensions of 46.85 mm in width and 0.16 mm in thickness. Also, the width of the slit was 28.61 mm, which was quite more substantial than the other tapes beforehand. The slit had to be quite a bit larger as duct tape overall was just stronger. During the test, the duct tape could hold 2.2 kilograms, meaning it held 21.582 newtons of force. Through these values, we developed a K1C value of 45.6, thus meaning the duct tape had a higher critical stress factor than the electrical tape. For masking tape, we had also tested it for its fracture toughness. We had decided to cut a side slit into it so we can physically see the differences between the materials. The masking tape had a thickness of 0.11 mm and width of 24.02 mm. The masking tape was overall the thinnest tape tested. Once again, we kept adding weights till the tape had failed, and we maxed out at 2.5 kilograms with a cut width of 5.65 millimeters. The weight resulted in 24.6 newtons of force putting stress on that masking tape. Through these values, we derived a K1C value of 51.4 MPa per meter to the power 1/2, which was the highest result we had gotten throughout all the tests. It could be possible that masking tape does not have a high elasticity, therefore resulting in a larger K1C value, as K1C values are often carried out for materials with a small scale yielding condition.
Upon testing each tape type individually, we also chose to construct a composite tape of one layer of electrical tape and one layer of masking tape. The consequential tape was the thickest by far at 0.25 millimeters, which alone led us to the hypothesis that it should carry the most load and result in the largest K1C value purely based on its lateral cross-sectional area. Like many composites, due to combining two different materials, we also proposed that the advantageous mechanical properties of each would work together to produce the highest result of any of the tapes tested. With a side split style cut at a width of 7.5 millimeters, the composite tape succeeded in enduring a force of 22.6 newtons before failure, equating to a K1C value of 37.3 megapascals. This result was not what was predicted at all and has left us questioning why masking tape alone produced a significantly higher K1C value while electrical tape alone was only marginally lower than the composite. Among possible reasons for these findings are that the loading method applied was not consistent across all tape types. This was due to the asymmetric design of the hook that was used to attach the weights to the tape samples, where the weight wouldn't be placed in the centre of the tape, causing load to be concentrated closer to the cut, inducing crack propagation earlier, while other samples the weight was placed more to the side of the tape without the cut, causing more force to be applied through that side of the tape and increasing the load needed for crack propagation. In future tests, using a symmetrical D or triangle style attachment point would ensure that the attached masses direct the load through the centre of the tape each time, providing better consistency and a more reliable method. It is also quite possible that in addition to the electrical tape, the masking tape had little to no advantage. As due to the electrical tape's extremely high elasticity relative to the masking tapes, it simply stretched while the masking tape took the majority of the load, and upon the masking tape failing, the electrical tape's fracture toughness had already been superseded.
When looking through a microscope, aluminium's failure surface shows important details about how it broke. The surface looks uniform with a grainy texture, which is typical of ductile materials. This suggests that aluminium stretched and bent a lot before it finally broke, which is common for metals bending under stress. The rough and grainy surface points in the ductile fracture, as you can see, means that aluminium deformed and absorbed a lot of energy before breaking. The lack of sharp and clean lines in the fracture shows that it didn't break suddenly. And these small dimples that you can see here are signs of how the material stretched and pulled apart at a very small level. For steel, there are visible surface cracks and fracture lines that suggest the material underwent a lot of stress, particularly tensile forces, which led to the formation of cracks running parallel to the surface. The roughness of the fracture surface and the crack pattern indicate a ductile fracture, as steel typically exhibits ductile behavior under stress. But we can see that the lower section of the sample appears smoother compared to the upper section, which could be showing the different regions subjected to tension and compression during bending, with tension causing more roughness, as we can see at the top. Timber is an anisotropic material, meaning its properties vary in different directions. We can see that the outer fibers are pulled apart, which is caused by tensile stress. The surface looks rough and uneven, suggesting that timber broke in a brittle way, meaning its fibers didn't stretch much before they snapped. The break seems to have happened both inside the timber and along the grain, with some fibers separating cleanly along the grain. Small gaps between the fibers show that they were pulled apart during the bending test, confirming that timber failed due to tension. Overall, the break followed the direction of the grain, and the way that timber's fibers were arranged played a role in how it fractured. And these beautiful images of carbon fiber actually reveal the fiber bundles breaking at different angles, showing a bristle fracture with little to no bending before breaking. The fracture surface is rough and jagged, meaning the fibers broke at different stress points, leading to the uneven edge seen in the images. Also, some fibers appear to have been pulled out of the surrounding material, indicating that the bond between the fibers and the matrix may have been weakened before the fibers broke completely. This often happens in composites where the material is stressed and the matrix fails to hold the fibers together. The overall brittle nature of the carbon fiber is clear, and as the fracture surface shows, there is no signs of bending or stretching before failure.